All right, welcome to the part two of the electron configuration notes video. Let's get into it here. So last time we learned how to do the standard notation electron configuration. That is using this diagonal chart, right? Writing everything out, every single orbital where all of the electrons go. Even for a very large element, right, you can do things in the standard notation, in which case you might get all the way down to here or all the way down to here, and you end up with a very, very long electron configuration. If you've done the practice problems that I gave you on the assignment, like that first part of the assignment, you probably saw that some of those can get quite large. So what we're going to look at today, two things. We're going to look at the noble gas notation. Okay, so how can you use noble gases to be a bit of a shortcut? Okay, and then we're also going to look at these things called Bohr models. Okay, and we're going to learn how to draw pictures like this for any given element. And so we'll do that towards the end of the video. Okay, but for now, let me actually zoom out of here. And let me go over to my periodic table. This is the same periodic table that you guys have. Okay, so yeah, that's probably a bit too much. All right, there we go. All right, so this is called, the shortcut that we're learning today is called noble gas notation. So what are the noble gases? I believe we've probably referenced this before in class, but just in case we haven't, noble gases are these elements over here in group 18 or column 18 on the periodic table. That would be helium, neon, argon, krypton, xenon, and radon. Okay, so these are the noble gas elements. And this method that we're going to learn today for writing electron configuration is called noble gas notation, because in each situation or in each problem, we're going to use a noble gas as part of our shortcut. Okay? And to illustrate that to you, let me go back over here and let me go ahead and do the electron configuration for a noble gas element. Okay, so let me do neon. Neon is right here. It's atomic number 10. Okay, so let me see here. Let me make this look a little bit better here. Okay, so neon is atomic number 10. The electron configuration for neon, we can determine that using the diagonal chart here. I'm going to do this a little bit quickly because I think, we spent quite a bit of time on this last time, so I think at this point you guys are probably okay with coming up with the electron configuration, the standard notation. Okay, so this is called the standard notation. All right, what we're going to do is we're going to learn how to write the noble gas notation. All right, and to show you how that works, I'm actually going to show you how that works on the next element up. Okay, so this is just the standard notation for neon, nothing new there. What I'm going to show you is how to write the noble gas notation for sodium. Okay, sodium is element number 11. Okay, so it's one more proton and electron bigger than neon. All right, sodium. All right, so it's atomic number 11. Now, before I show you exactly what noble gas notation is, let's just go ahead and write out the standard notation. Okay, so it would be 1s2, 2s2, 2p6, right? That would get us to 10 electrons, right? But then we have one more electron that we have to account for. So that would go into the 3s orbital, right? After 2p comes 3s, and that would be 3s1, right, for that 11th electron. Okay, so this is the standard notation for sodium. This is the standard notation for neon. The question is, how can we use a noble gas to shortcut this process? Okay, how could we shrink this up a little bit so where we don't have to write quite as much? And here's how it works. So this right here is the standard notation for neon. Okay, we're going to say that this can be represented like this, putting the symbol for neon in brackets. Okay, so this is the electron configuration for a noble gas for neon. So to write the noble gas notation for sodium, I'm going to substitute this part, all right, which is the same as the electron configuration for neon. I'm going to substitute that with the symbol for neon, and then I just have that one extra electron left over, right? So this right here represents this, the electron configuration for neon. Okay, and so that's what I've included. So that is Ne in brackets. Okay, so that's what I have here, and then this is the 11th electron. Okay, let's look at another example of that. Okay, let's look at the next noble gas, which is argon. Okay, so argon is number 18 on the periodic table. Let's write out the full electron configuration for argon. It's 1s2, 2s2, 2p6, 3s2, 3p6. Okay. As I mentioned before, I'm kind of a major nerd / dork, so I basically have electron configurations memorized at this point, which is really kind of sad. Don't be like me. Okay. All right, so that's the electron configuration for argon. You'll notice that they end with a very similar ending, right? So like neon and argon are both noble gases. Look how they end. They end with S2P6. This ends with S2P6. What you'll notice, by the way, is that as you go down through these noble gases, all of them end in S2P6. Okay. All right, so this we're going to represent with AR in brackets. Okay. So let's actually then write the noble gas notation for this next element, scandium, using this AR. Okay. So here's scandium. Okay. So here's argon, right, number 18. Here's scandium, number 21. If we wanted to use noble gas notation for scandium, what we have to do is we have to sort of backtrack and look for the most recent noble gas. Okay? So for scandium, I would definitely want to use argon. I wouldn't want to use neon, right? Because neon isn't the closest noble gas to scandium. Okay? But you have to be careful, all right? If we were doing bromine, for example, you would rightly think that, oh, krypton is the closest noble gas, right? Well, you're not allowed to go over. Okay, so it's kind of like Price is Right rules, all right? You have to choose the closest noble gas without going over. So if we were to do noble gas notation for bromine, I would still want to backtrack all the way back, and I would arrive at argon as well. Okay, so argon would be used for the noble gas notation for all of these elements here. Okay, just as how krypton would be used for all of these elements here. Okay, you have to look for the closest noble gas without going over. So you just sort of backtrack and go to the one on the row above. Okay. Okay, so let's go back here. Let's take a look. Scandium is 21 electrons. Okay, I'm gonna write AR. Okay, this represents this. Okay, which is 18 electrons worth of electron configuration. Okay, 18 electrons worth. So I only need to represent 3 additional electrons after this. Where should I start? Okay, well, argon ends with 3p6, right? So if I look on my diagonal chart, the next place that I would go for scandium would be 4s, right? And I can put 2 electrons there, 4s2. But remember, I had 3 additional electrons here that I had to account for. So after 4s, I get to 3d, and it would just be 3d1. Okay? So that is the noble gas notation for scandium, right? If it was 1 electron bigger, then it would be 3d2 or 3d3. You can keep going, right? But every noble gas notation has to have this noble gas at the beginning. And you can see how this is definitely a bit of a shortcut compared to something that's long like this. And it becomes even more of a shortcut as you get further down the periodic table, where you might have something that can't even fit in this box, right? But when you write it in noble gas notation, it can, be written very, very shortly, okay? So we'll get some more practice with this in class, but that is essentially how you do it. All right, let's skip over this slide. We're going to do some of these in class together. Let's look at Bohr models, okay, because this is the other thing that I wanted to look at today in this video. So what is a Bohr model? So a Bohr model is a diagram of an atom which shows the placement of the electrons inside the atom. And if you think back to the video from last time, I talked a little bit about Niels Bohr. He developed the first quantum mechanical model of the atom. So this right here, what you're looking at, is kind of a Bohr model, okay? What we're going to do is we're going to learn exactly how to make those for any different element, okay? So the electrons go in concentric rings, which represent the energy levels inside the atom. And using an element's electron configuration, you can construct a Bohr model for an atom of that element, okay? And I just have one slide to show you. We're gonna do like a real life example of this in class using my document camera, but just for the purposes of this video, let me show you what we've got going on here. So this is for the element sodium, okay? It's atomic number 11, right, which means it has 11 electrons. I've written out the electron configuration here. Sodium, an atom of sodium is going to have its protons and neutrons in the nucleus, right? But the electrons are outside of the nucleus. And we want to know, like, where are they exactly, okay? And more specifically, which energy level are those electrons in? Okay, that's actually what's going to that's actually what's going to matter for us, okay? Which energy level are they in? The orbitals have a number, okay? This is 1s2. 2s2, 2p6, 3s2. The number in the front of the orbital tells you which energy level those electrons are in, okay? So the first ring is the first energy level. There's only one orbital that starts with 1, right? It's 1s, and there are 2 electrons there. So to draw a Bohr model, we would need to put those 2 electrons on the first ring, okay? And so I've circled them there in red, okay? You would actually draw those 2 dots there on that first ring. That would represent those 2 electrons in the first energy level. For the second energy level, and for all the other energy levels, there is more than one orbital, okay, that could potentially have electrons. For sodium, we have 2s and 2p, both of which start with a 2, okay, so that means they're both in the second energy level. Even though they're different orbitals, they're still in the same energy level. And so those 2 electrons here plus these 6, that equals 8. That means that in the second ring, in the second energy level, there are going to be 8 electrons. Okay, and I've circled those 8 electrons there in the second energy level. And then lastly, for sodium, we only have 1 electron beyond that, right? It's in the 3s orbital, which is the third energy level, right? So I've got my 1 electron there circled in the third ring. Like I said, we'll look at actually doing this on paper. I will be having you draw some of these on paper, mainly because it's harder to do it on the computer, but also just because I want you to get in the habit of doing it on paper. So we'll look at some more examples of all of this in class. So thanks for watching, and I'll see you next time.